All right, so we're going to talk about data cleaning today. So come down to our materials and schedule. We are all the way down here, if you can believe it, all the way to day 5. So we're actually we're halfway. After today, we'll be more than halfway. So we've done an amazing job already, and we should feel really proud about that. Okay, just a little bit of a recap on what we've already talked about. So yesterday we did a bunch of summarization with Ava. We talked about how we can use the summary function to get quantile information. We talked about the count function, which is one of my favorite functions, and we'll see that it's extremely useful for checking our cleaning. And so that shows us how many unique values we have and the number that we have for each of those unique values. If we just want the distinct values themselves, we can use distinct. And there's also the n distinct if we want to know for a particular variable. It likes vectors, so we got to use that with full. We talked about group by, which makes all of our subsequent functions pay attention to specific groups. So it pays attention to a variable that we say we want to have groups recognized for our subsequent functions. And so we can use that with summarize to get means and sums and all sorts of things that we might want. And then we talked about how the n function can also give us a count as well inside the summarize function. All right. We also talked about data classes. We talked about how there's 2 types of numeric objects. We can have integer or double precision. So we'll see DBL as the class, or we'll see int if we're looking at a tuple. And the integers are just whole numbers. Double precision means we have a little bit more information. We have some decimal information. We have logic class that's true or false. And remember, we do not include quotes. Anytime we have quotes, that means we have a character. We can use class function to figure out what the class of an object is. And if we need to change it to be some particular class, we can use the as dot class. So as dot numeric, as dot character, etc. Talked a little bit about factors and how they're a special type of character that has levels. And we're going to be talking about that with its own module soon. So, get excited for that. Then we talked about how we have some more multidimensional objects. So we have our data frames and tuples. But we also have options like matrices and lists that we might see in the future. Not so much in this course, but you might encounter them. We also talked about dates and how the LuberDate package is extremely helpful for that. And that our last questions, if you did the practice for the date problems for class, the class lab, you'll note that, we need to have things in the date format to actually mathematically appropriately use dates. It's important to know about that. However, we know that not everyone is going to be working with dates. Elizabeth likes factors the best. They are incredibly useful, for sure. There we go. All right. So moving on to data cleaning. So data cleaning in general is a process of investigating our data and fixing any inaccuracies or recoding anything that we might need to make it more manageable, more readable, more understandable. So the first rule of data cleaning is you have to look at your data. You have to know if there's anything to clean. And a big piece of that is actually dealing with missing data. So there are a few types of missing data that we can have. We can have NA, which is just general missing data. It's sort of generic. We can also encounter NaNs, which stand for not a number. And that happens when you divide 0 by 0. I have this chunk here ready for later. So notice here, I get a NaN when I divide 0 by 0. You can also have infinity or negative infinity, which happens when we divide a number by 0. So if I divide 1 by 0, I get infinity. And if I divide negative 1 by 0, I get negative infinity. And there's a few functions that are helpful for looking for these. They work on vectors, like a lot of our mathematical functions. So isNA looks for NA and NaN. It's a little bit broader. IsNaN only works for NaN, and IsInfinite only works for infinite or negative infinite. So here we're making a little vector here that's got 0, NA, and negative 1. When we divide it by 0, we can make one of every type here. So we have a NaN, an NA, and a negative infinity. When we test with isNA, we're going to get true for the NaN and the NA. but not the negative infinity. So notice that this function will not catch infinity. So if you're using mathematical operations that are going to be dividing things by 0, you might need to worry about these. A lot of us are not, so then you don't have to worry about it, but we want to make you aware that that is a thing. And then, of course, nan is only going to find the nan values. So we get a true for where it's nan, and we get false for na and negative infinity. And finally, is infinite is only going to give us true for infinite, for the negative infinite value. So we can combine this with any. So in our vector, we have a nan, an na, and negative inf. It's going to, if we say is na any, it's going to give a single true or false statement about are there any na values in test. So each of these are going to give multiple responses for each value in the vector. It's going to give a true or false for every single value in the vector. Whereas when we combine it with any, we're going to get one single true or false for the full vector. Okay, so maybe we'll do something a little bit different over here just to observe some of that. I'm making a vector that has a single na value, and I'm going to say is na for that. Let's see what our output is. I get a string of false, true, false, 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 which makes sense. We have our true where our na value is. And if I use any with it, what do we think we're going to get? We'll get one value. That's correct. Will it be true or false? We can read this as, are there any NA values in test? And this is what test looks like, right? Test is over here in our environment. It will let us know if there are any true values. That's correct. Yes. So we have a single true statement, so we get a true. Now let's change this to be 5. Now what should we get? Correct. So we get false for everything. And because there is not a single true, we get a false for our any statement. Okay, very good. All right. So now let's try working with some real data. We're going to be working with our ER Colorado heat visits again. And we're going to first take a look at our data a little bit using the count function that we discussed yesterday. So I have the tidyverse here. I got to load that. And I'm going to read in this file using the read_CSV function from readr. And remember, we've got our quotes around our URL and our file equals argument. So when I run this, I get an ER object here. And I am going to use count on the visits column. And just a reminder, let's take a look at ER in general. So I can click on it in the environment. So we have these variables that we've been working with. We have the year, the visits, the confidence information about rate, the rate here, and the county. So we're looking specifically at the counts for the visits. So we see that we have 339 rows that have visits with the value of 0. So in our markdown, we can scroll through this giant table because we have 37 rows. So there are 37 unique values. And we can see that we have some NA values listed at the bottom. So count is really great because it gives us that NA information. There are some base R functions that give us tables like this, and they do not give NA. But I think it's really nice to be able to be informed about our missing data. There is really cool package, though, that helps us to especially look at missing data, and that is the Nannier package. And so that's not part of the tidyverse. You would need to install it first with install.packages and the name of the package, and then load it into memory. And it's a pretty quick package to install. Got to have the I in the word install, though. All right. And make sure it's loaded in memory. Good to go. So it's got some really nice functions. It's got many, many functions. So if we wanted to take a look at those, we could type in Nannier. It's going to come up with this suggestion with these 2 colons. When I say enter in there, it's going to show me all the functions in this package. Notice how to the right, we have this little curly bracket thing saying Nannier. That's so showing us that that's the package that it's coming from. So there are tons of useful functions. We're not going to go over very many of them. But if you work with a ton of missing data, maybe you'd like to learn more about them. But we're going to talk about what we think are the most valuable. So one of them is the percent complete, which tells you the percentage of a variable or data frame that is complete, meaning that is not missing. So if we run it on our R object, we see that 73, almost 74% of it is complete. So that's a pretty good amount. And then we can ask for particular variables. We can select particular variables. So we can say we're interested in the visits data and ask percent complete to check that. And we'll see that it is 60% complete, or the rate variable, and it'll say it's 60% complete. So let's try that for yet another variable. Like, I have a feeling that county is probably pretty complete. Let's just run this to remember what we're doing with select. So that's selecting a smaller tibble that only has county, and percent complete. Indeed, it is 100% complete. So we don't have any missing values from that variable. Okay, let's see if we want to check another variable. How about year? Year is also complete. Yeah, we're going to get to that. I love those questions because it's like so satisfying to respond with, yes, we will cover that. In fact, we're going to do it right now. So this is one of the most valuable functions. I think the percent complete one's nice if you're really focused on a particular variable or you want to know for the whole data set, but this one's really great. It's called miss_var summary, so missing variable summary. And it gets the percent missing as well as the number missing for each of the variables, and it gives you a nice table. So in this output, it gives us the information about which variable it's talking about, the number missing for that variable, and the percent missing for that variable. So note, this is the inverse of this, right? This is the percent complete. So this is what is not missing, and this is what is missing. And those numbers match up. So that's a good sign. So 0% is missing for county and year, which matches with what we saw. And we saw about 60% missing, complete for rate and visits. All right, so let's see what that looks like live in R. All right, so very, very useful function, I think. But sometimes it's nice to have a visual representation. And so there's also some really nice visual functions to make plots. And so I believe this is actually our first plot in the course, so it's kind of exciting. And it's quite simple. So we're going to use a function called ggmissvar, and we can actually just use it simply on its own. So ggmissvar, and GG stands for grammar graphics, which we'll see more of that kind of description later when we talk about plotting. So if I use the default setting, it's going to give me the number missing, but I find that the percentage is a little bit more useful. So there's an argument here, show percent equals true. So the default is false, but I think it's useful to actually have the percentage. So now when we do this again, we're going to get a pretty similar plot, but the thing that changed here is instead of the number missing, we now have the percent missing. And this matches with what we just saw. We have about 40% missing for these columns, and these two column or variables, year and county, have 0% missing. Because by default, show percent is set to false. And so if we exclude this, it's going to be the number missing. So notice, I don't know if you can see both of these simultaneously, but this is percent missing, and it goes up to 40% because that was the maximum percent missing. And this goes up to 300 because that was the number that was missing. Depends on what you're interested in. I think the percentage is a little more valuable. Now let's think about, what do these NA values really mean for us, and what are they going to do? So recall that when we do mathematical functions like sum and mean and median, we would get an NA value anytime we use those with vector that has NAs in it. So here we can see that each of these functions is getting an NA as the output for this vector, which has a single NA value. And that's also true if we have a logical vector. And R thinks of logical vectors as ones and zeros. So a true is considered a 1 and a false is considered a 0. If we have an NA value, that's going to also disrupt that. Just to prove to you that the summation does work like that, I'll show you that now. So let's see, we have 1, 2, 3, 4 trues and 1 false here. And we're going to ask for the sum of x. So we get a value of 4 because we have 4 trues. And if this was just falses, we should get a 0. But if we add any NA, no matter what, whether we have true or false, we're going to get an NA value. So just like we saw yesterday, anytime we have a mathematical function like this, we're going to want to use that na.remove equals true statement to be able to get the value where we exclude the NA value. So here we included this statement, and now we got the 4 because we had 4 true values that were summed. Okay, or over here, we can say sum na.remove equals, and we get a 0 because we have 0 true statements. We only have false. Okay, also, we did not tell you yet, but there's a thing about filter that you need to know, which is that filter automatically removes missing values. And that's because it doesn't know what to do with them. So the reason we're getting these NA values with these mathematical functions is when we try to sum this, our is like, well, this could be 600 or 6 or 0. I don't really know. So I can't sum that. Can't mean that. I can't median that. And likewise, when we filter, it's trying to meet that condition that we're asking for in our filter statement. And if it can't tell, it's going to give an NA value. It's going to just drop it, So that's important because you might want to keep your NA values, and that depends on your data. But I would say that often we typically do want to keep those. So let's see some examples here. If we use our filter statement, we're going to use visits greater than 0. So we have, when we do this, we're going to have a tibble of 126 rows. And we can see that our data set has many, many more, right? We have 768. So I can also just print this here so you can take a look at it. We have 768 rows if we don't filter for visits greater than 0. So is that because we just had a lot of visits that were 0? Or is it because we also maybe had some NA values that we dropped? Okay, so let's add this or is NA statement. So remember in filter, we could use or so that we only had to meet one or the other condition. So here it has to be visits greater than 0, or it's okay for it to be an NA for visits. And so when we preserve the NA values, we get back up to 429 rows. So in our original filter statement, we were dropping not only visits that were less than 0 or exactly equal to 0, but we were also dropping a lot of NA values. And we can see that again with our count function that we saw. We had 339 zeros. So we're dropping those when we say greater than 0. And we also saw that there were 303 NA values. So that's why we dropped so many when we filtered. So it can be really important to preserve these NA values depending on what they mean in your data. And sometimes it's a little unclear what they mean. Sometimes we want to get rid of them. And the way we can get rid of them is, of course, we do a filter statement that doesn't account for them. We let them get dropped. That's one way. But sometimes we don't have anything else to filter for. So we can use a function called drop NA. So again, don't do this if you think that you might need those NA values. But if you know that you're not going to need them, you know that they were maybe, for example, a situation where an NA value means that the instrument that was measuring air pollution or something just wasn't working that day, then you would want to drop those. But if it was that it was just undetectably low, then maybe we want to preserve those because those have some meaning. So we can use this drop_NA function on our variables that we want to get rid of NA values, and that will drop the entire row where there happens to be an NA value for that column. So let's see what this looks like. All right, so original data set here, we've got an NA value here in the first row. And if we add a drop statement, we will remove that row that we just had. So anything that's like that, where the value is NA for lower 95 CL, that entire row gets dropped. Notice, however, it's okay if we have NA values in a different column. We have only asked it to get rid of NA values for this particular column. And so here we can see that just printed out in the slide as well. Reminder that we can have NA values for other columns. However, we can also use the function on the entire data set. And this is like kind of nuclear. Like it's gonna remove every single row that has any NA value for any variable. So I find that this is not typically a situation that you might have, but it might be. And in which case, maybe you're doing a mathematical function where you really can't have NA values, then drop NA can be really useful for this. So anyway, when we use this, we get down to 463 rows because we have removed all of the NA values for any of the columns. So that's why everything looks complete. Notice previously we had some more columns, or some more rows, I mean. We also have a function called missVarWhich, which can tell us which variables have missing data, any missing data at all. So there can be one single value or 300. And so if we use that on our data here, we see that we have missing information for these columns. So year and county don't show up because they are complete. So we could say, oh, I want to get rid of a variable that has missing data. And to do that, we can use this function, the missVarWhich, in conjunction with the select function. So a couple days ago, we learned how we can select to remove columns with the exclamation mark. So select not missing variables, and we end up with just county and year. And sometimes we actually want to make an NA value. So say we have a value that's a 0 and it doesn't make sense. Like say it's a measurement where a 0 means that the device messed up. We can't possibly have a 0. Like nobody has a 0 blood pressure that's alive, right? So then we're going to want to change those values because something was wrong. So in this example, we're saying maybe we think that the person who entered the data made a coding error and maybe zeros don't make sense because we have a lot of those here, right? We can actually use a function called NAIF to create NA values from a particular value. So here we're taking the ER data set and we're using the mutate function because we're modifying a variable, right? Anytime we're modifying or making a new variable, we want to use the mutate function. And we are trying to modify the visits variable. So we want the current name for that variable. And we're going to say it equals NAIF for the visits variable, the current data for that variable, if it's 0. All right. And then when we do count on that, notice originally we had a bunch of 0 values for count, right? So let's do ER count, visits. When we do this on the raw data, we get 339 that are 0. Now that we've changed them to NA values, we're not seeing them here. So they probably turned into NA values. Let's take a look over here. So all I'm doing here is the same thing. I'm converting my NA values to 0 for the visits column, and then I'm piping this into count so I can quickly take a look at that. So if I go all the way to the bottom, I see that I now have 642. So I have increased the number of NA values. So it looks like it worked. And if I want to save my results, I would need to either overwrite my object, or in this case, I want to make a new one called ER0 so that I save that. Okay. We can also go the other direction. So we can use the replace NA function to replace NA values. Note that you must use numeric values for your replacement. We're going to talk about how to replace characters in the next half of the lecture. But if we're working with numeric values, we can do the replace NA option. So same structure, we need to use the mutate function. We're modifying that visits column. And in this case, we're reversing what we did. So we're saying that we want our NA values. So our NA values that we were seeing here to be zeros. Actually, this is working with the original data. So now we have twice as many zeros here as what we originally had. So let's take a look at with our ER non-zero data here and try that as well. So let's just examine what the data looks like again. We have no 0 values, right? Smallest visit value is 11, and we have 642 NAs. We want to replace our mutate. We want to mutate that visits column to change so that we replace NA where visits is 0. So we want to replace anywhere there's an NA like these to be a 0. Okay, and let's type that into our count of visits so we can see what's really going on. All right, now we have 642 zeros, and we should have 0 NAs. So we have successfully replaced our NAs with zeros. And this is something that you might do quite often, actually, because it's, like I said, not uncommon to have a situation where you're working with an instrument, and if it's below a certain threshold or above a certain threshold, it might not be, it might be that it's just a low value and we can think of it as a 0 or something like that. So think about your data first. It really is case by case specific. Sometimes removing NA values is going to lead to distorted math. Sometimes it's important to think about the denominator that you might be using for your math. Is it important to know how many values you had overall? Also, think about, is an NA something that's so low it couldn't be reported? Or is it that if it was too low, there's a different issue, like people didn't know what to write? In that case, maybe we want to keep our NA values because we're not sure what they mean. So here's another example. If you have a survey where students report NA if they've never tried cigarettes, but the survey reports 0 if a student has tried cigarettes but did not smoke this week, then we need to be really careful not to confuse those two groups of students, right? Because one of those groups is potentially smokers, but they just haven't smoked this week. And so they have a 0 value, whereas the NA are students who have never tried cigarettes. So we might want to keep the NA values. We might want to recode them into never smokers or something like that so that we can really interpret our data appropriately. Again, watch out for denominator changes, especially for percentages. It might be important to know how many total values there were. So here's an example of that. Here we're creating a percentage, and unfortunately there's not really a convenient percent function in R, which might seem kind of surprising. So we actually have to do this ourselves, but we now have all the tools to do that. So here we just created the count of the visits like we did previously, and we're creating a new variable called percent, where we take the n column and divide it by the sum of all the n's. So we're asking what percentage of visits were a 0 value or an 11, for example. And so, we take that division, the denominator is going to include all of our n's here and multiply it by 100. So if we drop NA values before we do this, we're going to see that zeros account for 72% of the data. But if we keep NA values, they account for only 44% of the data. So it's, that's going to be impactful. All right. Some common issues that might happen, challenges with extra or missing commas. It's always a problem. If you hesitate a little bit, R will give you some information. Like, notice it's giving me a little red here. Like, I don't know, that looks a little sketchy to me. And if I try to run it, it's going to give me an error about a parentheses. Similarly, for situations with a missing one, incomplete expression. Also be careful about how you refer to columns. If you misspell it or you give it different capitalization, if I capitalize visits here, it's going to say visits not found because visits doesn't exist. I only have a column that's lowercase visits. So watch out for those common issues. All right, gut check. What function can be used to remove NA values from either a full data frame or an individual column? Is it A, drop nulls, B, drop NA, or C, remove NA? What was the function we did? That's right. Very good. It's drop NA. So another reminder here that it can drop all the NA values if you just use it on the full data frame, or you can use it for a particular variable. All right, how can you keep NA values when using filter? Is it A, use the, I don't want to say it out loud because I'm kind of describing it. Is it A or B? Okay, so yeah, right. It is A. So we're saying whatever our condition is that we're trying to filter by, and it's also okay. We can have or, the value is NA. So our condition or, it is NA. If it was and NA, it means that it has to meet the condition and it also has to be equal to NA, which would not work, right? All right, in summary, there's a bunch of base R functions like is NA, and we have any. There's also an all function if you're curious about all of the values that can be helpful to check for NA values. but count is also really helpful. And then we also have nice summary functions from Nannyar that give us visuals or tables. This was that one that I really, really liked. Just a reminder of what it looks like. Gives us the number missing and the percent missing. Misvar, which is what we did to find out the names of the columns, and we can select against those columns. So we can use that exclamation mark to say we don't want those columns, we want to get rid of them if that's something that you want to do. Remember that filter automatically removes NA values because it can't confirm if an NA meets the condition that it's filtering by. So we need to use that for as NA to keep them. Drop NA is that really awesome function that helps us get rid of NA values if we don't want them, but we need to be careful about that and think about what they mean. NA if will make NA values for a particular value, and replace NA will replace NAs with a particular value. So if we want NAs to be 0, for example, we would use replace NA. Our first step here is going to be reading in the data and a little bit of review. We're going to want to use read underscore and the URL to get the data. And of course, don't forget to load your packages. And you might need to do this step of installing Nannyar. Read it in and assign an object so that we can keep working with it. Let's call it CES. Okay, so we're going to call it CES. And to assign that, we're going to use the assignment arrow. We're going to use read CSV and file equals. And I'm going to copy this URL and I'm going to need quotes around it. I did a little trick here. I selected the URL and then I clicked on quotes, and that puts the quotes around the whole string there, which is nice. All right. And you might see some information about delimiters. Delimiter's apparently a comma. We've seen this data before in our other labs. Might be a good idea to, take a look at the data, remember what we're working with. And question here is use the isNA and the any functions to check if the lead variable has any NA values. And we want to use the pipe operator to do that. And we get a hint that we need to do the pull function because these functions only work on vectors. And the lead variable is an estimate for the risk of lead exposure in children living in low income communities. So we scroll around. This is a really big data set. We've got a lead variable here. And this is our general format. I'll give you some time to try that out. All right. So we're working with our CES data. See that here in our environment. And we're going to pipe that into everything we want to do next. We know that we need to use poll so that we get the vector version. And what's the column that we're working with? The lead column, right? And I like to just check my work. So I'm going to just make sure that this is what I expect just for this part. All right. So I can see that that looks like the values I'm generally seeing for the lead variable here. And then I'm going to say is NA. I expect this to give me lots of true or false values. Indeed, I have a lot of true or false values here. And then I'm asking, are there any true values in this giant vector of true or false? And the answer is true. So what does that mean? Do we have NA values or not? That's right, we do. So you can think of this like a sentence. In the CES data, we pulled out the lead data. We asked, are there NA values? Were any of them NA values? And the answer is true. All right, next question. Clean the rows of CES so that only rows remain that do not have missing values for the education variable. Use the drop NA function and assign this object to have ED data. And so the education variable is the percentage of the population over 25 with less than a high school education. So I'll give you some time to try that out. All right. So the first part that we'd want to do is figure out the object that we're going to assign. And the last statement here says assign this object to have ED data. I'm going to just copy this and put my assignment arrow. Next thing I know is that I'm working with the CES data. So that's the next step I'm going to add. And I am going to be dropping some NA values. I'm going to pipe this into the drop NA function. And I'm removing missing values from the education variable. So if I were to just run this right now, this would remove all of my NA values, and I don't want that. Just want to remove rows that have NA for education. Put the education variable inside drop NA. So this is going to take our CES data and drop the NA values from this education variable and make a new object called have_ed data. Right, we can't use filter without a condition. But if we had a condition that was like filter education, let's see what education looks like a little bit. Search is not very good, is it? Anybody know where the column is?
It's it's on the second half.
Thanks.
Yeah, you're going to have to scroll now because,
It's like all the way back there.
Okay.
Yep. Oh, there it is.
Thanks.
Yeah.
All right. So we can kind of see a sense of the ranges here, and we can see that we do have some NA values, but I could do something like I want to have an education greater than 0 or greater than 3. And when I do that, it's also going to drop the NA values. Unless I have, in the case like what we're doing right now, maybe we want to keep everything else. We're okay with 0.4. We just want to get rid of the NA values. But I appreciate that you're trying other things too. That's great. Right. So we can see that our original data set had 8,000 observations, and now we have 7,932. So we definitely dropped some rows. And, if we wanted to check things, we could do something like % complete. So we could take CES and we could pull, actually % complete likes tables. We could select the annoying education and check if that's complete. So in our original data, it's not complete. So we had NA values, which makes sense. And in our have_ed data, it is 100% complete. So that fits with what we're expecting. All right, question number 3 here. Use Nannier to make a visual of the amount of data missing for each variable. Use ggmissvar. Check out more about this package here. And remember, we can do an argument about whether we want to see the % or just the missing values, which is the default. So I'm going to give you a moment to try that. Yeah, it's kind of a cramped graph. There's a lot of columns. We'll learn how I can show how we can make it a little bit easier to see. All right, so we're using ggmissvar and CES, and I personally like the % argument. Remember the argument, so I like to use my documentation, show %, right? And you can do it either way. And indeed, when we do it down here in our Markdown preview, it's going to look pretty cramped. When we print out a report version, it's not so bad, but also we can try it directly down here in the console, and it's going to put it in our plots pane, unless we've had it set up like Ava has it set up, and then it would automatically do that. But I let it do the preview here. And we could click on this zoom button, and my computer has been having challenges, but there we go. I don't know if you can see the pop-up. Can you see the pop-up? Okay, let me try to share the extra piece here. Wait, no, that's the wrong one. Where am I? Sharing everything. Okay, see it here? It's still kind of squished. We can stretch it and we can get it to a place that we like. I think that's pretty good. And then we can right click it and we can say copy image or save image. So we could make it however we like the dimensions to be. And we'll learn later that we can also do fancier things in saving a file like that too. But this plot zoom is pretty nifty for that, I would say. Don't you think? All right. So that is it for the first part of the lab. There's some practice questions here to do some more. Moving on to recoding variables. So we did kind of technically a little bit of recoding already. We talked about how we could change NA values out if we had a numeric column. So where we could go to an NA from a numeric value or from an NA, both directions, right? With our NAIF and replace NA functions. But sometimes we have character vectors that we need to recode. And sometimes we need to do more complicated things than just our NA values. So we're going to be working with some data about that I made up. It's not real data this time, but I needed it to be messy so that I could show you all these recoding options. And it's basically as if we measured the level of different microplastics in the blood of someone who eats fish versus someone who does not. And there's a lot of articles here about microplastics if you're interested in that, as this is, of course, Daisy, and we're interested in environmental health. So you can read in this file from the website using our typical code, the read CSV function. I clean this off too, so we have a little bit more space. All right, and let's take a look at our data. All right, so we have information about the type of foods that people eat, information about the different microplastics that were measured. And you might notice that there's some things here in terms of the way that they're coded, that there's some differences, and we have some blood levels. All right, so we have 4 variables. We have a start blood level, a nanomolar, and a change. Okay. And so first, let's just take account of how many unique values we have for the microplastic column. And that'll give us a sense of how many odd ways we have things written. And so I saw a question earlier. We can either type our data into whatever we're doing, or we can also just type it directly. So they're just 2 different options of ways we can do the same task. So we can see here that we have BPA abbreviated as BPA, or we also have bisphenol A, so where it's written out. We have dioxin capitalized, dioxin lowercase, and we have lowercase BPA. We also have other and O, which we're going to assume represents other. So we've got a lot of recoding that we would like to do if we want things to be consistent, right? And unfortunately, some of you are probably going to encounter some data like this at some point. Okay, so you could use Excel and go in and manually change them out, but I highly recommend that you don't do that. I saw there was some questions, I think it was in a survey response, about, that you could do this sort of thing, and it seems hard to do in R. I'm hoping by the end of today, we don't think it's as hard. The really cool thing about R is it's very reproducible and clear how we recoded our data. Whereas if we do it in Excel, there's no record necessarily. There's a record if we have a separate file and we keep track of every step that we did. We might make a mistake. Whereas in R, we can check our code and it's right there. And there's a really cool function. It's actually my favorite function. It's called case when, and it's extremely helpful for recoding our values in our variables. And some of you might know about if-else statements and things like that. And so it's kind of like that, but it's all wrapped together, so we don't have to worry about that kind of thinking. And so it's really flexible and powerful tool. Important to note that you're going to need mutate to use it, because we're going to use it to create or modify variables. Okay, so we're going to walk through this slowly. I know there's a lot on here. We're going to recode things. So we're going to create a new variable so that we can check our work from the existing microplastic variable. So just like typical, we're using the mutate function, writing the name of our new variable, and then an equal sign. And in this case, after the equal sign, that's when our case when function comes in. And then inside the case when function, we're going to do conditions, kind of like filter. But the difference here is when we specify a condition, so in this case, microplastics is exactly equal to capital O, we're going to use a tilde sign, which is it's actually the backtick key. So it's the key in the upper left corner on your keyboard under the escape key. And that's telling us if we have this condition, then we want it to be this. So I want it to be replaced or recoded with the phrase or the word other. Notice that I have some quotes here. I have quotes around the values for my variable. I do not have quotes on the names of my variables, just like we talked about with filter. If R knows a variable is already there, it doesn't need quotes on it. But anytime we're talking about character strings or pieces of character strings, we're going to need to have quotes. Okay, so we have one condition here, right? And we have a few other exactly equal to conditions. We have when it's bisphenol A, let's make it BPA. When it's lowercase, let's make it capital BPA. When it's lowercase dioxin, let's make it uppercase dioxin. Okay, so let's see what happens when we do that. We're going to put it into the count function so we can easily see how we changed our data. We're specifically looking at the new variable that we're making and the existing microplastic data. Because remember, our data looks like this, where we have a microplastic variable. All right, so let's take a look at just what happens when we do this first step. All right, we have our data, but now we've added this new variable, right? Notice that there's some NA values, right? And when we look at our count version, we see that we've got some NA values for capital BPA, capital dioxin. Those seem to be the things and other. Those seem to be the phrases that we wanted, right? So what happened here? Well, there's one extra step in case when that we need to know about. That if we don't specify all the conditions we want, we're going to end up with some NA values. So how can we avoid that? We didn't specify what happens to values that are capital other, capital dioxin, and capital BPA, right? We don't see them here on the left of our tildes. We don't have any conditions for those. Well, there's this true statement that we can add, and that's the value that we're going to get if we don't meet any of the above conditions. So if we want to keep the existing values, we can type in the name of the variable that we're working with. So here we're working with the microplastic variable. We say if it's true that it's none of these conditions, keep the original data. And now we don't have any NA values. And so we get this beautiful recoded data here. So let's see what that looks like now. Ooh, that looks better, right? Now we don't have those NA values. Looks like we've got complete information and it looks nice. Maybe we want to use relocate to move this variable right next to our old one so we can see the difference. Otherwise, we can use that count function, right? So let's try that. Let's pipe that into the count function so we can check. Let's look at our original microplastic variable and our microplastic recoded. Notice that we're combining here a mutate and count. I just piped it into it. If I wanted to save the data, I've got to be careful. I don't want to save the count version. I just want to save this part. But this is useful for checking the data quickly. So now I can see that I have converted the rows where I had bisphenol A written out into BPA, etc. But again, if I want to keep my data, I'd want to assign this to maybe plastics recoded or something like that. Or maybe I'm okay overwriting, and so I'll just call it plastics again. And that'll help us keep the new variable that we just made. Any questions about that at this point? We're going to see more examples, so that'll help a little bit. So and all of that, I think, already. Yeah. Oh, so in this example, we can actually simplify things a little bit by having the true statement. You know, there is the option that you could actually write out every condition that you have, but the true statement helps us keep it a little bit simpler so we don't have to duplicate. So we could have like capital BPA stays as capital BPA, but that true statement is quite useful. All right. There's another way that we could do this. Remember in filter, we also sometimes used this in operator. And the in operator allows us to check for if our value is in a vector of values. And so instead of listing out each of these, I could say lowercase BPA or this one, blah, blah, blah. I have a single line here that has all the different variations for the ways that I'm seeing BPA, and I want those to be coded as BPA. Or all the ways I'm seeing dioxin, I want that to be coded as dioxin. Okay, so let's take a look at that. I'm actually going to try it. I redundantly have a true statement here because I believe, recoded everything. I have a statement for everything here. Oops, I want this to be uppercase dioxin. Let's fix that. It looks pretty good, right? And I don't have my true statement. But what if I missed something? It's useful to have that true statement just in case I had some NA values or, I don't know, some special values that I missed. So I'm a big fan of just including it no matter what. Oops. but I messed up my parentheses. So I need this parentheses, the end of the case when parentheses to be after my true statement. That part's a little tricky. And then this is the closing parentheses for the mutate function, right? And leaving my true microplastic statement, I could even get rid of these values, right? Because those are already the way I want them. I get rid of this. Technically do that later, but and that's because we already had this version in our initial microplastics, right? But however you want to do it, as long as you're writing out what you're changing is fine. I think this is a really readable way to say that I'm okay with these two versions and I want it to be coded as this or that. All right. Another reason for case when is it can do some sophisticated things. So sometimes we want to create a new variable that's going to be based on another variable. And case when is really powerful for this. So let's say we wanted to make a new variable that has to do with the effect. Like we're making a text version of the blood level change. So we can say if the blood level change is a positive number and it is greater than 0, we want to call it an increase in the amount of microplastics. If it's exactly equal to 0, we'll want to make a new value that's same. And if it's less than 0, we want to decrease it. So we'll have the value of decrease, right? Because a negative change would indicate that we have a decrease in the amount of microplastics. Question? Yeah, like could I do this column minus another column kind of thing? Yeah, I believe you can do that. Yeah, it just has to be a condition that R can understand based on the columns that you have in your data frame. Yeah, we'll try to include a fancy example like that on Slack after this. I'm just writing a note. Often we can get away just with a mutate. So we might not need case when, because mutate would allow us to create a new function, a new variable, and it could be equal to blood change level minus start, for example. And that will give us the value that's the difference, for example. And I find that likely meets a lot of the needs that we have for that. But sometimes maybe you want to take that and then also transform it into some sort of text like this. All right, so let's take a look at this as well. So in this case, we're again making a new variable effect, and we can see that it matches up with what we thought. We have our positive values showing increase and a negative value here showing decrease. And if we had a 0 value, it would be same. Okay. And then that can make it easier when we have a text version of things. This is really useful for making visuals, making tables to better understand or interpret our data, because sometimes numbers are a little harder for us to interpret as humans. So here we can look at the count of foods, the type of foods that the person eats, and the effect. And we can see that for a diet of B, eating B foods, we see always an increase. Whereas with A, we sometimes see a decrease. But we're generally seeing a lot of increase. Okay, so gut check here. We need to use what function with case when to modify or create a new variable? Is it A, modify, B, select, or C, mutate? That's right. And I feel like this is the trickiest part about case when is remembering that we need to use it inside of mutate. But remember that it's helping us recode the either modify or create a new variable. So we need mutate. Very good. If we want unspecified values to remain the same, so if we don't have a condition for a particular value in our variable and we're using case when, how should we complete the true statement? Should we put the name of the variable that we're using as the source, or should we use the word same? Nice. Yeah, that's right. We're using the word, the name of the variable. So let's go back to see what that looks like. So in this case, just in case we have any other values for microplastics, we're going to want to keep those. So we say true tilde microplastic, which is the name of our original column. And just to reiterate how we think about this, I like to think of it as a sentence. I am mutating to create this new variable called microplastic recoded, which is equal to the case when the microplastic data variable has a value within this list, then create it to be this, etc., etc. All right. We're going to shift now to working with strings. So what we've done so far is recoded entire values, right? In our tables, looking at our microplastics, we've recoded an entire value from capital dioxin or lowercase dioxin to capital dioxin, or bisphenol A to BPA. But sometimes maybe we have partial string things that we want to do. And for that, we're going to use a package called Stringer, and that is part of the tidyverse. So anytime we load the tidyverse, we automatically get Stringer loaded into memory, which is nice. And it helps us modify or find a part of a character string. So we don't have to worry about the whole character string, which makes it a lot more flexible. You might be familiar with some base R functions or even Unix or other types of language functions that are, or commands that are like grep or gsub. We're not going to talk about those, but those are really similar to what we're doing. And every function in the Stringer package starts with str. So if I type in str, I can see a bunch of Stringer functions. So remember, the curly brackets here indicate what package the function's coming from. And there's a ton. There's a lot of Stringer functions. Can just keep going. But we're going to talk about the few that are the most useful. And honestly, I typically use, I would say, about 3, and don't usually need the others very often. So some of the most useful Stringer functions are str detect and str replace. And they look for a pattern, a piece of a value that's character within a character variable. And they work with vectors. So they don't like data frames or tibbles, which is kind of the annoying part about Stringer. But we'll show you how you can use it in a seamless way with case-when and with filter. So str detect is great if we want to just look for a pattern. So we're detecting, we're finding if a pattern is found, and str replace replaces a pattern. So let's take a look at some of these in action. So remember, these functions work on vectors. So we have to use pull if we're going to isolate this. So we're going to pull out the information here to get our data. I think there might be a mistake here. So I would want to pull from my plastic data the effect column. And I can't remember if I ended up saving this or I just printed it. I think I just printed it. So before I do that, let's make sure, notice when you copy paste from the console, you'll get these little plus signs. R doesn't like those. So I'm keeping my work here. I had it down here. How silly. But anyway, I'm keeping my work so that I have that variable. So if I take a look here, you can see that I indeed have the effect variable because that's what I want to work with. And I'm going to make an effect vector that's going to be pulling my plastics effect column. Or we could think of this a little more clearly, I think, is taking the plastics data set and piping that into pull. Right, now I see a vector here. Take a look at it. It's got increase and decrease. So it's got a lot of character strings that I can work with, which is great because that is what the Stringer functions work with. So just to see what they're doing here, if I do str detect, I have a few arguments that I have to put in here. I have to put in a string argument. And again, these are one of those arguments, or these are the arguments like we've seen in some of the R functions where we don't have to specify it. It'll just assume based on the order of things, but it's important to, I suggest that it's better practice to often include the arguments because sometimes they're required for a particular function. And even if they aren't, it's a much easier thing to read here because I can see that I'm using the str detect function to look at the string effect, and I'm looking for the pattern D. So it's useful to include all of those arguments. All right, so it's a little tricky because our strings here we're seeing mostly falses here. because we're looking for a D here. Let's look for, we have a lowercase d here. Let's look for ink. All right. If we do ink, you can see that ink shows up for most of my strings, but not for this one, right? Or if I do C, I'm going to get one true here for this value. So it's searching for part of the string, and it doesn't have to be a word or anything in particular. It could be just a piece of a word, and it's going to search for that. Notice that it is case sensitive. So lowercase d, we don't see in any of our values, but capitalized D, we do see for this value. This can be super useful if we want to replace part of a string. So str replace helps us do that. It's very similar. We have our string argument, our pattern argument, and we just add a replacement argument here. So in this case, we're replacing capital D with lowercase d, and it only replaces those patterns. There's also a function called replace all, and when we use str replace, it's only going to change out the first time we see a pattern. So here I'm asking it to change the lowercase e into capital E. And notice each of these words has letter E twice. So only the first E gets changed. If I want to replace all of them, I need to use replace all. But note that the all here is talking about the instances within each value. It's not talking about the values in the column. It's talking about the actual value itself. Inside the value, how often do we see that string pattern? So taking a look here, it's not talking about how many times we see the word increase. It's looking at each individual cell. We're at the cell level now. Do we see the letter E multiple times? It's a little bit of a tricky concept, I think. Another thing that can be really useful is str sub, which is for subsetting, and it helps us to take just a piece of our string. And this is a pretty common need because sometimes we have a variable or values in our variables that have extra information that we don't need, right? And so we can say, I only want from a starting position to an ending position of what I want to keep for a string. So in this case, remember, original values are increase and decrease. I'm only taking the first three values. So we're thinking of this as 1, 2, 3. So let's see how that works a little bit in more detail. I'm going to print out our vector so we can kind of see what's happening here. So let's change this to start on value 2. If I start at value 2, it's going to just give me the second character and the third character here. I could even just do a single character. So I start and end at 2. Okay, but the real power, I think one of the most nice things that we can do with Stringer is combine it with filter. So, because right now we've just been looking at vectors, which is somewhat useful, but we're typically working with data sets, right, in our tables. So let's say that we want to find rows where microplastics have a letter B in them. We can combine the filter function with str_detect, and instead of having to have the perfectly spelled, correct, exact value, we can just do part of the string instead. So in my example over here, I'm going to do BP. So I'm only going to get rows that have BP in the microplastic variable. So our string here is the name of the variable, and then our pattern is, this pattern BP. Or if I did A, I get more results. I'm going to get bisphenol A as well. This is great because sometimes we have, complicated bacteria names or something like that. And it's hard to not make a mistake with typos. And this is really helpful for that. Back to our original problem. Now that we know about Stringer, let's try to put some of this together. So recall that we have a lot of strangely formatted names here. And we had used Casewin to recode some of this to make it more consistent. It's possible that we might miss things, right, because of misspellings. And we have our true statement, which is great. That's going to keep our values and keep them from turning into NAs. But there still might be incorrectly coded content, right, or values. And so if this is a super complicated thing and we have, really complicated, disease names, bacteria names, pollutant names, this might be a useful time to do this. So we can improve what we did with Stringer to make it more flexible. So what we're doing here is we're nesting stringer inside of case when. So we already saw how we could do it with filter right here, because remember it works only on vectors. So here we can use it inside of case when to make improvements to how we are recoding things. So the str detect here is looking for within the microplastic variable, do we have a pattern where we, in this case, start with a lowercase b or a capital B? So notice that or operator we've seen before from filter, and we are introducing some special ways of working with the string here, where we can indicate either the beginning of a string or a $sign can be the end of a string. I find that the beginning can be quite useful if we're dealing with complicated spellings or something. So we can say, look at the microplastic variable, look for patterns where we start with either lowercase or capital B, or in this case, lowercase o or lowercase d, or capitalize O, capitalize D. And when we have that, make sure it's DPA. If it's O, make sure it's other. If it's D, make sure it's dioxin. And then if we have our true statement, just to be careful here, and we can take a look at the result. And we see that it also worked where we have everything recoded the way that we wanted. So we can try that over here as well. Yeah, it's going to, that I believe is a typo. Good attention to detail. Okay. It ends up not causing a problem for us because the capital B here got recoded. I'll have to look into that a little bit more. We'll put some stuff on Slack for these. Obviously, more complicated problem. Yeah, I thought we had capitalized bisphenol A though, but let's try looking at just the microplastic recoded count. Nice. It looks good. Great. It might be that this ends up being redundant. I think that might be what's happening. Yeah, I think the statement just works for the full string, and that's why it works. Yeah, maybe. We'll look deeper into that. Yeah. Okay, so just explaining to everyone, what he's saying is that we're looking only for the letter B, which can be anywhere. But we wanted to point out that you can actually use this to look for a specific location. But it's okay because B is, even though it happens to be at the start, we're looking for a capital B anywhere. And so that's why it still recodes. All right. So we know this is some complicated work. We're going to have some easier examples in the lab. I feel like they're a little easier. To try to incorporate some of these ideas and see them in practice with some more data. Okay, so what stringer function helps us find a string pattern? Is it str replace, str find, or str detect? What did we talk about? str detect, that's right. And if we weren't sure, we could type in str and see what we have here. So we're going to talk about separating and uniting data now. And so this is relevant to what we've been talking about because sometimes we can create or unite columns together to make a new one. So it's got a really great name, Unite, for uniting columns. And it has a few arguments that we want to include. So we have a column argument, which specifies the new column that we're creating, the name of that column, the separator column, which is what we're going to be putting between the things that we're smushing together. And by default, it's going to be an underscore. And a remove argument, which specifies if we want to drop the old columns. And I believe the default is true. So for example, here, we're going to take, let's look at our original data. We've got now this effect column and a food column. We can unite those two columns together, even though they're on total other ends of our object here. And the column that we're going to make is going to be called change. So this is our new column. and we say remove is true, which means the foods column goes away and the effect column goes away. This is what it looks like in our output, where we have an underscore between those pieces of information, the information that came from the foods column and the information that came from the effect column. Okay, so we can take a look at some of this over here. We can try something slightly different. Let's try microplastic and we'll do effect. All right, so now we have increased dioxin, decreased bisphenol. We have gotten rid of these columns. We only have 4 columns now: food, change, blood level start, and blood level change. And we have an underscore between them. The tricky part about this one is mostly just remembering the columns or the arguments that you need to put in, and that this argument is for the name of the new column. Yes, it is the default. So we can try something else. We can say separator equals semicolon. Yeah, we can do that. There we go. We can do this. All right. And then I think what's even more useful actually is separating the columns. So it's not uncommon for us to get data where we have really 2 pieces of information in a single column. And it's often hard to try to do calculations or plot specific aspects about that if they're lumped together. So the separate function is especially helpful. And it basically works in the opposite direction of our unite. So it splits a column into multiple columns. In this case, we have the column argument specifying the column that it's going to split up. So it's not the name of the new column, it's the column that it's splitting up. Whereas the into argument specifies the name of the new columns. And then we have our separator argument, which again is going to be default of underscore, I think, but we can specify other things as well. So here we are taking our change column that we just made, which had our foods or diet information and increase. And we're going to change that into a foods column and a change column. And that's going to get rid of our original column by default as well. So the change column goes away and we end up with this separated foods column and change column. Okay, so let's try an example of this one as well. I'm actually going to do something a bit, actually, let's do this. Save this. Okay, so I made this new United Plastics that had this new variable in it, and let's try to now separate it. So we're going to take our United Plastics data set and pipe it into the separate function. And we're going to say that we're using the column. So notice that the column, in this case, it was creating the new name. In this case, it's the column we want to modify. That's a little bit tricky, I think. The column we want to modify is our change column. I don't need quotes around it because it already exists. In this case, it did not. And I'm going to say into, and my new column names, I've got the effect and the microplastic. So into effect and microplastic. I'm going to call it micro this time. And because I have 2 things here, I need to use my combine function. And then I can specify the separator, which in this case I need to do because it's a little unusual. All right, let's take a look at that. Okay, so that created a new effect and micro column, and it got rid of our change column. And now they are separated back to the original form. Okay, any questions about this? All right, it can be a really useful function because sometimes we need to separate out information. So I find this one very useful. The thing that I forget about it is that we don't need mutate here. This one works all on its own. So it's, and the way I kind of think about that is it's sort of just modifying the existing variables a little bit. But for me, it's a little bit tricky to remember that I don't need to use mutate for this. Okay. So we talked about some of the trickier topics of our entire course. So you should feel really good that we got through that. We're going to do some lab to practice it. But we talked about case when that does require a mutate. And that's for working with data frames and tibbles to recode. We can recode entire values based on conditions. So if we don't use it with stringer, we have to use the entire value. And we have that statement of true tilde something, usually the name of the variable, if we want to keep it, those existing values. Otherwise, they will be changed to NA. You might see a function called recode, and it does a lot of what case-when does, but not everything that case-when does. So we don't typically teach it because we feel like it's easier for you to just focus on the one more powerful function. But you could see it out in the world, and we have some extra slides at the end if you want to take a look at that. So remember, case-when, if you're used to if-else statements, it's kind of like that. I like to think about it as sentences. So take your original data, type it into our mutate function because we're making or modifying a variable, specify what that variable is that we're either making or modifying, and think of it as the case when if a certain condition is met, then change it to this. Otherwise, all of these conditions are not met, do whatever the true statement says. Okay, then we talked about the stringer package, and we had all those str functions that are really useful, and they work with parts of our character values. So they're really helpful when combining with filter. We use filter with str detect inside of it, then we don't have to have everything perfectly written out. We can just do part of the values that we're searching for. And it's also got some other helpful things that we can do, like str subset, if we want to subset part of the text. And we talked about str replace, or replacing the first instance in a value, or replace all for replacing all instances. And so we talked about how stringer works on vectors. So we need to either combine it inside filter or case-when to use it on our data frames. And we also talked about separate and unite. They do not work inside mutate. They work on their own. Separate can split columns into new columns. Unite can combine columns. And we didn't talk about this, but you can actually use a colon to specify a range of columns. So you specify the start column and the end column, and it can actually mush together a lot of columns at once. And I like to do that when I'm working with sometimes address information. So I'll get lots of different columns that will say maybe the street and the state and the zip code and all of that. And if I need to make an address, I will unite all of those columns together. And I'll specify the starting column and the ending column with my colon. So it'd be something like, I'll show you an example. So we had up here, take a look at our plastics data again. We could, for example, unite all three of these. Kind of silly, but we can. So we're going to unite foods to blood level start. So they need to be right next to each other for you to be able to do this. And that's going to be uniting everything that's in between. And I'm just going to print this so we can see it. All right. So that put, our colon as our separator, or we could change it out to this. And that's putting all three of those columns together. And that worked because they are right next to one another. So all of these are next to each other. This would not work if they're not next to each other. All right. Looks like we answered the question there. Are there any other additional questions before we jump into the lab? Got some cheat sheets here too from Posit and from us as well. So if you work with a lot of strings, I highly recommend checking it out. It'll show you little examples of all the things that you can do with strings, as well as what's called regular expressions, which is getting into more of the weeds. That was when we had our caret and our $ type stuff. All right, we're doing all right then? Ready to practice? I think practice for me is always what makes me really understand it. So let's try that out. So got the lab here. I will copy that link address. Should be the same one. So unless someone's joining us late, just keep with what you had. And we are starting on part 2. This is all we're doing today. So it's just this lab here that we have left. And the first thing we're going to do is just run a chunk. So we're imagining that we work in a clinic and we're trying to understand information about blood types of patients and whether they got an infection. And we're going to use the Tibble function to create some columns in an object called blood type. Okay. And so then we see some output about it. We have a column about whether they had exposure to something, what their blood type was, and with if they got an infection. Notice we have some inconsistencies here, right? We have yes written out, we have no written out, we also have Y and N, we have capital letters with lowercase, and we seem to have a tiny bit of some variation in our type data even. Got some lowercase stuff. So we're gonna have to fix those. So one of the first things that might be useful is to determine how many NA values there are for exposure. And we're going to assume that anytime we have an N or a capital N or lowercase n, that's a coding for no. So that's not an NA. We talked about lots of ways to look at that. Use your favorite type of way. All right. Anybody want to share what function they're using to try to look for NA values for the exposure variable? If you want to, share it in the chat. Love it. And we talked about a lot of ways, right? We could use a nannier function, or we could use baseR or dplyr. I personally really like count because it's really simple. Yeah, gonna look like what we had there. So blood type is our data set. Exposure is the variable that we're looking at. You can see that there is one NA value. Lots of options. And we're specifically looking at the count too. Yeah, there's lots of ways to check if we have NA values. I love seeing all the variety of ways that people like to do things. It's really cool. All right, so we know now that we have some NAs, right? So we want to keep that in mind when we're recoding and think about whether we want to keep that information, drop that information, right? So our next question here is recode the exposure variable, which we know has NA values, so that it is consistent. And we're going to use the case when function, and we're going to assume that other is something we want to keep. That's not like an NA value. So we're going to keep that as other. And we have the general format for it because we know it's a very complicated one. And just a reminder, when you're working with your data and you find like, oh yeah, I think I need to recode something. I think I need to use case when, you could come to our slides and be like, I'll go to the cleaning slides and find the general format for it and recreate it. Or you could look up the documentation. So you don't have to remember all of it. It's more about the intuition of understanding the logic that you need to do. Okay, so I'm going to give you some time to try that, and then we'll check it out together. And again, if anybody has any, sticking points, getting any errors or anything, feel free to message. All right, how are we doing with that one? I know it's a lot. It's a tricky one. This is our hardest problem, I think. Are we ready to go over it as a group? I don't want to go ahead of anybody if they're working through it and want to. Give me a thumbs up if you want me to go through it now. Got 2 votes from what I saw. Elizabeth, did you see differently? Because I'm sharing the screen. It's a little hard.
I realized that the way I have my screen set up, I couldn't see any votes. So yeah, whoops.
I saw 2, which is not a huge percentage. So I'm going to wait just a little bit longer and then I'll go over it. Okay, let's try this out now. Okay, so let's take it one step at a time. We know that we need to assign our object. So let's just recode. So it's okay to overwrite. And we're going to use, actually, I'm going to test it out. So I'm not going to put the assignment stuff until a little bit later, until I've looked at what I did. But we know we don't need our blood type data, right? Over here. And we're going to pipe that into our mutate function. And we are recoding exposure. We could make a new version of it, or we could recode to create a new one. I'm going to make a new one just so I can see everything really clearly. And then I can see I need equals case when. And I also like to separate out the lines. I put that enter sign in, and that makes my parentheses that close case when and mutate down here. So I don't have to worry about them anymore. And I am recoding the exposure variable. Okay, that's our variable that we need to recode. And let's take a look at it again. We've got some, looks like capital N, capital no, lowercase n. And we've gotten a suggestion here that we could use the in operator as a way of working with all of these different codings. And with the in operator, I always need my combine function to list out all the different options. So we've got capital N, capital N-O. I don't know if there's any capital N-O like this, but you know what? I'm gonna put it in there just in case. I think there's some lowercase n's and some lowercase no's. And so anything like that, I think should be no. I like the uppercase like that. So that's what I want to do for that. oops, I accidentally opened my options. And I need a comma between each of my statements. And I also want a code for yes. So I'm going to take the exposure variable and use the in statement and see what I have for that. Yep, looks pretty similar. So let's say yes. Let's make this consistent with our code above, just for ease of reading. So capital Y, yes, written out with a capital letter, yes in all caps, lowercase y, and lowercase yes. And again, I might not have these values, but I'm just being careful. I think that they're possible that they're in the data set, or they might be in the data set in the future, and we might be getting more data. So I'm going to include that there. And then I don't want to make any new NA values because I know that I have some real NA values. So I'm going to include that true equals or true tilde exposure so that I can keep my original values. Okay, so let's see what that looks like. All right, is this consistent? It's pretty good, I think, but might want to check it. But that's our next question. So I'm not going to check it yet. I'll let you try to figure that out. But let's reassign this or save it to a new data set or something. Since we made a new variable, we're in pretty good shape here. So I'm just going to reassign and overwrite my existing blood type data. Okay. And I can double check that I've got my new variable and it looks pretty good. It's pretty small, so I can actually see what all the variables are or values are, but that might not always be the case. So the next question is, how can I check to see how many values for each category I have? So to answer the question, so anytime we have the exactly equal to, we have to do that for each individual statement. So that would get pretty long, but we'd have to put exposures exactly equal to for each of those. But good thinking. The one at the others, that would work. That would keep all of our others as is. The line about other. That is okay. So I'll give you a tiny bit of time for 2.3 because giving you a pretty nice hint. It's fairly simple. All right. So this one is a little bit easier. We're going to use count, and I kept my data set same. I just overwrote it. Yours might be different, so keep that in mind. Maybe you made a new data frame here, and you need to check that one. And I'm going to check exposure. We'll just try that exposure new, because I made a new value here. I'm going to try just exposure new, and then I'm going to also look at count exposure, comma, exposure new for both of those. All right, this looks nice. This is exactly what I wanted. I have no always as capital NO. I have other still. I have yes, the way that I wanted it, and I kept my NA value that was real. All right. And if I wanted to, really see how it all worked, I could include that other initial column, which you may or may not have because maybe you overwrote it. But this helps me check that I recoded things the way that okay. And now number 4 is recode the type variable of the blood type data. So we have a type variable here so that it's consistent. And we're going to use case when again. And we have a hint here about what the inconsistency is, that there's sometimes lowercase o's and sometimes capital O's. And don't forget that we need to use quotes for our values here. And that extra step that we include at the end of case when we want to be careful about things. So recoding the type variable here. Looks like we've got a couple of lowercase o's that we want to fix. Yeah, there's a shortcut if you select it and then actually don't use them. I know Ava uses them all the time. I think it's control shift enter or return.
Okay.
Actually, it looks like that will run the entire chunk. Just the selected line is control enter. The only reason is I actually looked, if you go up to run.
Happening multiple lines. There we go. This works.
Yeah. If you go up to run, and click the arrow up at click the arrow. I have to look it up every single time because I never remember.
Yeah, notice here, this is what she's talking about. But my muscle memory is so fast with some of these things that I haven't needed the shortcuts. Can be helpful though. All right. I think I'm going to go through this one now. This one's a little bit simpler than our last one. So I'm going to use my blood type data and pipe that into everything I'm doing. I'm using case when, so that means I have to mutate. And I'm concerned with recoding the type variable this time. So I'm going to recode type, and I'm using base when, and mutate always has that equal sign of like what we're modifying and the source of what we're doing. And I like to just get my parentheses out of the way by pressing enter. And I'm working with the existing type variable. And this time we might want to do what people had in the chat for our last example we were trying to do, Jocelyn was trying to do. Might want to do exactly equal to a lowercase o, and I'm going to recode it to be capital O. I got to get my dot and my negative so that I'm not replacing anything there that I might need. So let's, I'm trying to replace this one and this one so that they look like this and this. So that should fix that one. And for anything like it, I'm going to fix lowercase o positive, and I'm going to specify that that goes to capital. Okay. And then I'm going to put my true statement, and I want to keep anything I had for type just in case, because if I don't specify it, I'm going to end up with NA values, right? So actually, let's just see what happens if we don't do that. I know that we need it, but let's see what happens. Whoa, I ended up with a lot of NA values, right? Because I only specified a couple of conditions. So I don't want to do that. I want to keep my existing type information. So when these conditions are not met, when that is the case, when that is true, keep the original type variable data. Okay. And then I'm keeping my original parentheses. They're closing my case when and my mutate. Let's try that. That looks nice. Okay, so I'm going to save this. And now I'm going to check my results. I know that you just did that, so I'm just going to go over this one. So I like to use count, and I'm looking at my blood type data, and I'm looking at, all right, looks like I have only these values. That looks correct. Okay, and our last question here, make a new tibble. So we're going to make a new tibble from blood type called blood type split that splits the type variable into two. So it's going to split this variable into two variables. And we're going to call those new variables blood type and RH factor. So I think you might be able to see why this could be very useful if we wanted to have a plot about RH factor and we didn't care necessarily about blood type, or we cared about blood type, but we didn't want all this extra RH factor information on there because it really just mattered what the blood type was. This would be really helpful to have. So note that periods are special characters. They are interpreted as wildcards by R. So we're going to need this double slash thing here in front of it as our separating character. So this will be our separating character. And make sure you use quotes around the separating character. Okay, so I'll give you a little bit of time to work through that problem. All right, so let's try this one together now. All right, so first things first, let's think about the data that we're making and that we're using. We're supposed to make a new data object called blood type split, and that's coming from our blood type data. And I'm piping that into the separate function. So we didn't have to remember that separate does not use mutate because we got this here, which is nice. And we are going to be working on the type variable. So that's the variable that I want to split, right? And then, so I could use the column argument if I want for that one. Into the columns, and anytime I have more than one thing, I know I need that combine function, and I need quotes for the names of my new columns because they don't exist yet. So they're going to be called blood type and RH factor. All right, and I'm not done yet because I have to specify the separator. That's going to separate the type variable, this one, and it's going to make blood type and an RH factor variable. Okay, so I need to add my next argument with a comma, as I usually do, and my separator I know is going to be this because I was told to do that. And I can see that here. All right. And just got to make sure all my parentheses are closed. Sometimes it takes a while for R to update too and make sure it's got everything that it needs. So if you have like an error symbol and you're like, wait, I don't think anything's wrong. Sometimes there isn't anything wrong. You just need to give it a second. But I can check my parentheses. This looks right. I'm going to cut that out for just a moment just to check it. And it looks like it worked. So I'm going to save my results. Nice. Okay. And then I can take a look at blood type split. And indeed, my blood type is now a column and my RH factor is now a column, which is much nicer to work with.